Hey y'all, CJ Berg here with Develop EV, and today we're going to be talking about one of my favorite topics, which is transformers. Whether you're new to the EV industry or you've been a long-time developer, you know that these can be some of the most difficult parts of the project. So we're going to talk about the 10 top things that you need to know about transformers so you can be successful. All right, so first off, we got to talk about what is a transformer, right? So these are things that are found all throughout the electrical system in North America, and the primary function of these is to step up or step down voltage. Voltage is the electrical pressure, or is the pressure of the electrical system. So this is what's key for any project, because most people in most projects can't actually take the primary voltage from the utility, right? That's way too high voltage, and all the electric vehicle charging projects that most of us are going to be doing in North America require much lower voltage to operate. So the three voltages that we generally find in North America are 120/240 split phase. That's what's going to your home or a small business or a small gas station, something like that. You have 120/208 three phase, and this is something that you have for this complex, for example, or something different. Or you have 277/480, which is what we're mainly going to be using when we're building DC fast charging projects, right? We need that 40 volt power to power our DC fast chargers. So number two is the components of a transformer. So these things look very mundane, very blocky for a pad mount transformer, right? But there's actually critical pieces of infrastructure inside of this that are critical to the operation of a transformer. So inside of this, there's gonna be oil for insulation. So you'll sometimes see a sticker on here that says like non-PCB or PCB, and that's basically just telling everyone around here what kind of oil's inside of this from an insulation standpoint. In the back side of it, there's going to be primary and secondary windings. So depending on how these windings are orchestrated, whether there's more on the primary side, less on the secondary side, or vice versa, determines if this is stepping up voltage or stepping down voltage. And between those different coils, there's going to be this iron core. It's this big piece of iron. And that is really there to kind of help guide the magnetic field between the primary and the secondary side of the transformer. Another part of the transformer that's kind of really important to know is there's actually a fuse that you can use to disconnect the primary side from the secondary side of the transformer. It's called a bayonet fuse. And different utilities will call it differently and things, but really what that is, it's going to be on the primary side or maybe on the high side of the secondary side, and the lineman will actually use what's called a hot stick to pull that out. So it will actually disconnect the primary side from the secondary side. So then the lineman can then go and work on the secondary side of the transformer, make their connections, all that kind of stuff. And then simply put that back in and then re-energize the secondary side at a safe distance with the hot stick. All right, so number three, we're gonna be talking about the difference between radial and loop-fed transformers. So if you're pretty experienced developing EV charging infrastructure, you probably already know the difference, but really it's very important to know the difference between radial and loop-fed if you're developing EV charging projects, because depending on which one you have and which ones are already on the property will depend on how easy it is to put in the new transformer for your DC fast charging project that has probably so much load it can't be tapped out of the existing transformer. So with a radial fed transformer, you can tell this by the primary side bushings. So on a transformer itself, the left side, if you're facing it, is always gonna be the primary side, and then the right-hand side is always gonna be the secondary side, which then will go to your project. So on the primary side, if there are just 3 bushings on that side, you can only see 3 lugs there, that is gonna be a radial fed transformer. But if you see 6, then you know that's gonna be a loop fed transformer, because then the primary is coming in, going into the transformer, going into the primary and secondary coils through that iron core to the secondary side. But then also on a loop fed, if there's those other bushings there, it then can go out to another transformer, another service. So depending on which one you have is really important to know for your project. All right, so number 4, we're going to talk about the general 2 different kinds of transformer. So the first, as we're standing next to right now, is a pad mounted transformer. So as the name suggests, it's a transformer mounted to a concrete pad. So these are what we're going to generally find for most DC fast charging projects out there, because we require such high load for these electric vehicle charging infrastructure projects that the small little overhead transformers that we'll see, that's the second different kinds for residential homes or small commercial buildings, can't satisfy the load that we need for DC fast charging. In general, anytime you go above roughly 500 kVA in size, you're going to need a pad mounted transformer. Sometimes though, you can creep up to 750 kVA depending on the utilities, ESRs, but for the most part, anything under 500 kVA is going to be an overhead transformer. Anything above that is going to be a pad mounted transformer, as we see here. All right, so number 5, we're going to talk about sizing transformers. So the size of a transformer is very important for your EV charging project to match your load as best as possible from the utility side. So transformers are sized in what's called kVA, and we're not going to talk about the specifics of that in this video, but in future ones, we'll get into all the weeds of that. But for 120, 240 transformers that you'll see for residential, commercial, those are sized between 25 kVA and about 167. 122 weight, 3-phase, that'll go from roughly 150 up to about 1500 kVA. And then for 277, 480, 3-phase transformers, that'll go from roughly 150 all the way up to 2500 kVA for secondary services. But some electric utilities throughout the country will actually have larger 277, 480 volt transformers, such as Southern California Edison has one that goes up to 3325 kVA, Pacific Gas and Electric is 3750 kVA. So those are big, juicy transformers that are great for EV charging projects because then you can get a higher load to that. But these sizes are super important, and really that size is determined by the utility, not as much the customer. We give them the load for our EV charging projects, and they go behind the scenes, do their own diversification calculations, and then come back and tell us what they're going to size their transformer to serve our load. It's not always one-to-one. It's not what we have to do on the customer side with the National Electric Code. They can kind of do what they want when sizing these transformers, and depending on what they do can create limitations sometimes. If they undersize your transformer, there's only a certain amount of peak load that you can reasonably hit, because you can't just run these things 150% of their rated capacity for too long, because they'll burn out, they'll break down. Even though there's no moving parts, it is still a piece of equipment and it can fail over time. So it's really important to work with your utility when you're doing your DC fast charging project or other projects in the EV space to make sure that these transformers are sized properly for the current and future load of your projects. Number 6, we're going to talk about customer versus utility side responsibilities for siting these transformers. So it might look like this transformer is owned by the building behind us, but in reality, it's always going to be owned by the utility for secondary services. It's important that you work with your utility when it comes to developing your project from the get-go, because there's going to be certain things that are responsibility as you as the customer developing this project, and there's going to be certain responsibilities that the utility does, and that's all lined out in the ESRs, the electric service requirements for each utility. And unfortunately, they're all different. They're not like one-to-one. It's not like the ones right next to one another. Different utilities are the same. They're always going to be a little different. So it's really important that you, as the developer and your engineer of record, understand those when you're developing your project. But in general, what the customer side responsibility is putting this pad in an area that's agreeable by the utility. Also, sweeping out primary conduits to wherever the utility is going to be intercepting them. Sometimes that goes to a primary pole box. Sometimes that goes to the bell hole of a switch. It can be different locations depending on what the utility wants. And then on the secondary side, you have to sweep out those conduits as well, going out to wherever your switchgear is going to be located. So it's really important that you put this transformer in an area that makes the most sense for both you and the utility. And there's a complete understanding between the engineer of record, the utility, and also the construction company that's going to be building this for you on where this is going to be located. Very important. Number 7, bollards and clearances. So as much as you'd love to put this wonderful piece of steel in the corner of your property, fenced off behind a bunch of bushes, you actually need to maintain certain clearances in the front, sides, and back of the transformer so your electric utility can safely maintain this transformer on your behalf. So generally speaking, you need about 10 feet of clearance in the front, 3 feet of clearance on both left and right side, and about 3 feet of clearance in the back. So as you can see here, there's this curb cut, this curb that's roughly, I'm going to say, 3 feet in front of this transformer, but the utility is actually able to give them a little bit of grace here and use this as part of the clearance, because if a car is parked here, it can leave, right, in a certain period of time. So they don't always need to have this 100% of the time clear. But the biggest thing is, within those clearances I talked about, you can't have permanent structures. So that telecom box over there is getting real close to that 3-foot mark, if not kind of intruding on it. So that could potentially be a violation. And if you do put things that are within those clearances and you're trying to develop your project and get that green tag from the utility to then move forward and basically energize your project, you know, they'll either tell you to take it out or they'll just rip it out themselves. I've actually been on projects before where I was going out with the, when I was working at the utility, I was with the linemen. We went out to a site and some lady had put these really nice palm trees in front of the transformer to try to hide it. And we had to get in there and maintain it. So we ended up having to come through and cut those out, to obviously not the, you know, best solution for the homeowner, but we had to do that to safely maintain the transformer. So it's really important that you keep this all clear. And when it comes to bollards, that's also very critical. So we're in a parking lot right now. It's a Sunday, there's not many people here, but occasionally there'll be cars coming through here, and it's at such a low speed that the utility probably didn't think that bollards were required to protect this piece of equipment from car accidents or other things bashing into this, because you do not want to hit this with your car. Bad things will happen. So the electric service requirements from each utility will call out where and when they want where they want bollards, but occasionally the utility might want bollards in areas where you didn't, or in times where you didn't expect, just because they, you know, they're going to play on the safer side. And honestly, for EV charging projects, your transformer is probably going to be pretty close to where vehicles are going to be parking, so it's always best practice to maybe err on the side of caution and put those bollards. So on the sides, those will always be, generally speaking, right, depends on the utility, will be fixed, poured in place, concrete bollards. And then on the front side, those will be removable for the most part, because the utility understands that you can't just put bollards in the middle, you know, always give 10 feet of clearance to put bollards on the front end of that. They kind of give a little leeway, so you can put bollards maybe 5 feet out, but those are removable. So when the utility comes to maintain it, they'll unlock those with their system key, put those to the side, and then they're able to maintain the piece of equipment. Number 8, procurement of transformers. So if you have developed EV charging projects in the past, you already know that getting the utility to buy these at the time that you want them to is one of the most challenging, frustrating parts of these processes, because you as the developer and the future customer don't own this, right? This is owned by the utility for secondary services, right? Primary metered services, where you're taking primary voltage from the utility, you'll actually own these, but for most of the projects in today's day and age, you're taking secondary service from the utility. So there's only so much you can do to coax the utility to buy these transformers at the time that you want them for your project. Lead times for these today can sometimes be a year, year and a half, 2-3 years in some cases that I've seen. So most of these charging projects you want to get done in year and a half, 2 years, and sometimes the utility just can't make that happen. So most times the utility is going to buy the transformer for their project or allocate one from their inventory when you sign the contract. So once you've done all the development work, you've agreed on where things are going, the utilities had a chance to engineer their side of the system, your engineers had their time to engineer their part of the system, everything meets up, contracts are signed saying, I'm willing to pay X amount, I'm willing to go forward with this project and receive power from the utility company. That's sometimes when they'll actually buy the transformer. And this can be 6 to 9 months into a project, not right when you file your initial utility application. So extremely important to know that going in, to understand that bottleneck, and then also work with the utility as much as possible to get things expedited, sped up, get contracts signed as early as possible so the utility can buy this on your behalf. Number 9, we'll talk about impedance of transformers. So transformers are not perfect, you know, conductors of electricity, right? There is some resistance to flow of current through them. And for most secondary services, utilities will have, you know, between a 5 and 6% impedance on their transformers. And this is really important to know so that your engineer of record on the developer side will know how to protect your system if there's ever a failure on the utility side, so they can catch the fault before it goes down further into your system. The utility can also give you that fault current information, but it's always important to know the impedance of the transformer that the utility is setting so you can kind of anticipate and calculate the worst case scenario. We'll do a whole video about the difference between asking for that current from the utility or just doing what's called an infinite bus calculation to model your system off of the worst case. Number 10, we're going to talk about flood zones. And if you live in a part of the country that has a lot of rain, hurricanes, thunderstorms, things like that, you probably already know that this can impact your project, but they also impact the location of your transformer, because just like on your side as the developer, your switchgear, your EV chargers, you never want those in harm's way if there's ever a flooding event. Just like the utility doesn't want theirs in a flood area in event that there is some sort of cataclysm or a 100-year flood event. So really important to work with your engineer of record, your civil engineer, your surveyor to make sure where you're putting this is not an area that is prone to flooding, pooling of water, or other things, because it doesn't take an expert to know that water and high voltage electricity and current it isn't a recipe for success, and it's not safe. So even this one is actually a little low. I actually probably would have put this pad up maybe a foot or two and not put this curb cut here so water can flow in it, so that this transformer is going to be isolated during high rain events. This also could have been used for drainage too, but how this parking lot's angled and stuff, the water is actually going to flow pretty much right into this transformer, which isn't ideal. So work with your utility engineer, your engineer of record when you're building these projects to make sure you're putting your transformer in a safe location that isn't going to be prone to flooding of water of any kind. Another thing that we're going to talk about is the difference between delta and Y transformer. So for EV charging projects, we actually always will need Y service. You can get away with delta sometimes with some electrical trickery, but we'll get that in a whole different video. And that really means that there's going to be a neutral coming out of this transformer. So on the secondary side, there's going to be 4 bushings: XO, X1, X2, and X3. X0 is actually going to be your neutral that's bonded to your ground bar in the transformer itself on the secondary side. And then the X1, X2, and X3 are going to be your 3 phases going to your project, assuming 3-phase service, right? So that's really important to know, because if you're in a very rural area or maybe a small little municipal utility or a co-op in the middle of nowhere, they might not actually have a Y transformer. So that's going to be really critical to know before you get into your EV charging projects. So your engineer of record knows that they'll have to do some stuff on their end to accommodate the fact that there's not going to be a neutral that's going to be provided by the utility.